We have seen two limitations of the conventional vacuum tubes when we try to operate them at the microwave frequencies. One limitation comes from the effect of parasitic elements, the parasitic capacitance and inductance, and another limitation comes from the transit time effect, electron transit time from cathode to grid. Conventional tubes have another limitation in the form of gain bandwidth product. For ordinary tubes, the maximum gain is generally achieved by resonating the output circuit. So, if we consider the circuit here, we see that there is a resonator circuit, RLC resonator circuit present, and what we assume now that omega Lk is very less as compared to the plate resistance Rp. For Rp very large compared to omega Lk, the maximum voltage gain Mx, which become V output by Vg, and this becomes equal to Gm by G, where G is equal to 1 by Rp plus 1 by R. Now, this particular condition occurs at resonance. Now, we find out the bandwidth around this resonant frequency, where the gain, maximum gain becomes 1 by root 2, and if we find out the bandwidth, then it will be approximately G by C, and therefore, a max product of Mx and bandwidth is equal to Gm by C. Now, we find that for a given tube and a resonant circuit, we have the right hand side independent of frequency, and therefore, if we want to maximize the gain, we will have to do it at the expense of bandwidth. So, for this type of tubes, higher gain can be achieved at the expense of bandwidth. In microwave devices, either resonant cavities or slow wave structures are used to obtain high gain over a broad bandwidth. So, we have discussed the major limitations which prevent the use of conventional tubes like triodes, tetrodes or pentodes at the microwave frequency range. And next we will see how specially designed tubes which operate at the microwave frequency and they provide high gain, they can be operated over broad band of frequencies. So, we start our discussion on microwave tubes with a 2 cavity Klystron. So, this type of Klystron tubes are used as amplifiers. Here we have a cathode which is heated and it emits electrons which are accelerated by the anode, and these accelerated electrons pass through the anode. We have two specially designed cavities, and here the cavity walls are made narrow, and also the electrons can pass through it. RF input is applied at one cavity which is called the buncher cavity. This is buncher cavity. We will see that the RF input applied here will help to form bunches of electrons. Separated from the buncher cavity by a distance L is the catcher cavity, and these bunched electrons while passing through this catcher cavity will deliver energy, and the oscillations in the catcher cavity will build up, and finally RF output is taken out from this cavity. So, as a result we will get an amplified version of the signal at this RF output. The electrons, after delivering their energy, they slow down and they are collected by the collector. Here we have two scales, one showing the distance z and another showing time t. So, at the instant t0, the electrons will enter the buncher cavity. At the instant t1, they will leave the buncher cavity. It may be noted that in this region there is no electric field, and this is the drift space. So, the emitted electrons from the cathode, they come to the buncher cavity, and RF input applied at the buncher cavity, we will see that they will produce velocity modulation resulting in bunching of electrons, and then these bunched electrons, they will move in the drift space, and finally when they pass through the catcher cavity, they will deliver energy to the catcher cavity, and finally they will be collected by the collector. So, these are the bunched electrons. So, let us first see the operation of this type of tubes in brief, and how the transit time effect is utilized here for producing velocity modulation of the electrons. The two cavity klystron is a microwave frequency amplifier which operates on the principle of velocity and current modulation. All electrons injected from the cathode arrive at the first cavity with uniform velocity. These electrons passing the first cavity gap at zeros of the gap voltage pass with their velocity unchanged. So, if it happens that the electrons appear at the buncher cavity at an instant when the RF signal is going through its 0, at that time the electron's velocity will remain unchanged. Electrons passing during the positive half cycle of the gap voltage undergo an increase in velocity, and those passing through the negative swings of the gap voltage undergo a decrease in velocity. So, depending upon the voltage present at the gap, here we can see that when the RF voltage is present, the electric field will either accelerate the electrons or it will retard the electrons, and when this electric field here is 0, the velocity will remain unaffected. Now, when we have the electrons, they are now moving with different velocities as they leave the buncher cavity. If it happens that the electrons which entered the buncher cavity in some earlier instant of time, they have been slowed down, and the electrons which entered the buncher cavity at a later instant of time and they got accelerated, then these electrons, the first moving electrons after some distance will catch up these slow moving electrons which entered earlier, and we will have a bunch of electrons formed. So, as a result, the electrons gradually bunch together as they travel down the drift space. Now, the variation in electron velocity in the drift space is known as velocity modulation. Now, as a result, since there are bunching of electrons, at some instant of time the density of electrons will be higher, at some instant of time the density of electrons will be lower, and the electron density in the second cavity gap varies cyclically with time. Therefore, the electron beam that passes through the catcher cavity, the second cavity, contains an AC component and is said to be current modulated. Now, if we want the power transfer from the beam to the field in the catcher cavity, the maximum bunching should occur approximately midway between the second cavity grids and during the retarding phase. So, when the second cavity field has a retarding phase, it will deaccelerate the electrons and the field will grow. So, energy will get transferred from the electrons to the field. The kinetic energy is thus transferred from electrons to the field of the second cavity. The electrons emerging from the second cavity have reduced velocity and are collected by the collector. So, because of this energy transfer from the electrons to the field in the second cavity, the field in second cavity grows and we have amplification of signal possible. let us now discuss some features of two cavity klystron, and also let us do some simplified analysis of this type of klystron devices. The main characteristics of a two cavity klystron amplifier are as follows. Its efficiency is of the order of 40%. The power output, we generally talk of two types of power output. One is the CW power or continuous wave power. It can be up to 500 kilowatt, and if it is a pulsed power, that means the klystron is delivering power over a brief period and then it goes off, then again deliver power. So, in that case the peak power may go as high as 30 megawatt at around 10 gigahertz of frequency. So, the pulse power, it is the power delivered over a very small period of time, followed by another period when the device essentially does not give any output power. So, it is the duty cycle which will decide the average power output, and power gain that can be achieved with this type of amplifier is again of the order of 30 dB. So, 30 dB power gain means a power gain of 1000. While carrying out the simplified analysis of this type of klystron devices, we make the following assumptions. The electron beam is assumed to have uniform density across its cross section. The space charge effects are negligible. So, when we will have a beam of electron, there will be mutual repulsion, and those effects are not considered here. The magnitude of the microwave signal input is assumed to be much smaller than the DC accelerating voltage. So, the input signal that we put in the buncher cavity, its magnitude is considered to be very less as compared to the DC accelerating voltage between the anode and the cathode. So, assume that the electrons are just emitted from the cathode because of the cathode being thermally heated. We have, after being accelerated through a voltage V naught, the kinetic energy half mv square is equal to E V naught, and therefore, we can write the velocity of the electron after being accelerated by a voltage capital V naught is given by under root 2 E V naught by m. E is the electronic charge, m is the mass of the electron. So, when these typical values are substituted, we get the velocity of the electron to be 0.593 into 10 to the power 6 under root capital V naught meter per second. Let the applied microwave signal be Vs is equal to V1 sin omega t, and as we have already mentioned that V1 is very less compared to V naught. Now, this voltage Vs will appear across the buncher cavity, and since the spacing between the buncher grids is kept small, we can see that as the electron pass through the buncher cavity, it will experience an average voltage that can be calculated by integrating this signal from the entry time t naught to exit time t1, and therefore we can write tau, which is d by V naught, is equal to t1 minus t naught. So, this is the transit time, and theta g, this is the transit angle, is omega tau, is omega d by V naught, and average microwave voltage that it experiences at the buncher gap is 1 by tau T0 to T1 V1 sin omega t dt, and when this integral is evaluated, we can write average voltage to be equal to V1 sin theta g by 2 divided by theta g by 2 sin omega t naught plus theta g by 2. We define a parameter beta I, which is the beam coupling coefficient, and its value is given by sin theta g by 2 divided by theta g by 2. Now, this voltage, average voltage, is the extra voltage that the electrons they experience during their passage through the buncher cavity, and depending upon at which instant the electrons enter the buncher cavity, this average voltage will vary, and therefore, now we can write velocity of the electron at the time of exit T1 is 2 E by m. Earlier it was only V naught, now it is V naught plus beta I V1 sin omega t naught plus theta g by 2, and if we take out V naught, then it becomes 2 E V naught by m 1 plus beta I V1 by V naught sin omega t naught plus theta g by 2. Now, this parameter beta I V1 by V naught, it is the depth of modulation, because depending upon this we now find that apart from this velocity 2 E V naught by m under root, which is the dc component of the velocity, or V naught, small v naught. This will now change because of this factor, and since we have assumed that V 1 by V naught is very small compared to 1, and beta I is sin theta g by 2 divided by theta g by 2. So, it will also be less than equal to 1. Therefore, this entire term will be very less compared to 1, and then we can write root 2 E V naught by m is equal to small v naught, the velocity of the electron only under the applied DC field, and here we can do a Taylor series expansion. So, this is approximately V naught 1 plus beta I V 1 by 2 V naught, this half is coming from this square root, sin omega t naught plus theta g by 2. So, now we find that the velocity v at t 1, it is having a modulation, and if we write everything in terms of t 1, then we can write V t 1 is equal to V naught 1 plus beta I V 1 divided by 2 V naught sin omega t 1 minus theta g by 2. Now, this is the diagram where we explain the effect of this velocity modulation, and we have already mentioned that when this velocity modulation is present, the slower moving electrons which entered earlier, they can meet a faster moving electrons which enter later. So, here we find that at time t a, the electron entered, it experienced a retarding voltage and it slowed down. At this instant, the buncher cavity grids did not apply any field. So, the electrons move with the same velocity V naught. Here at T c, the electrons experiences an accelerating field and this electron moves faster. Now, when we have this type of a scenario where we have the earlier entering electron is slowed down and later entering electron, its velocity is increased. After travelling some distance which we are denoting by delta L here, they will meet each other. Now, this time is marked as T d here, and this is representing 1/4 of a cycle. So, this time is capital T by 4 and which is equal to pi by twice omega. Now, we have seen that V t 1 is equal to V naught 1 plus beta I V 1 by 2 V naught sin omega t naught plus theta g by 2. Therefore, the maximum velocity that an electron can attain is when sin omega t plus theta g by 2 becomes 1, and therefore, V max has been denoted as V naught 1 plus beta I V 1 by 2 V naught. Similarly, when this sign becomes negative, the V min minimum velocity is V naught 1 minus beta I V 1 by 2 V naught, and we can write delta L, this is V naught into T d minus T b, or it may be written as V min into T d minus T a, or it can also be written as V max into T d minus T c. Now, we can write T d minus T c plus pi by 2 omega. So, this is actually T d minus T b, and this is same as T d minus T a minus pi by 2 omega. We also find that V max plus V min is equal to 2 V naught, and V max minus V min is equal to V naught beta I V 1 by V naught. So, using these relations, for example, we can multiply here by V min, we can multiply here by V max, and then V max T d minus T c can be replaced by V naught T d minus T b. Similarly, this side we can multiply it by V min. So, with this type of rearrangement of terms, we can find that delta L, which is equal to V naught T d minus T b, V naught into T d minus T b, and this can be written as V naught pi capital V naught divided by omega beta I V 1. So, this gives us the expression for the distance where the bunching occurs, and we mentioned that we want the bunching to occur at the middle of the catcher grid and at an instant when the phase is a retarding phase. Delta L gives us an expression for the distance where bunching occurs. Let us see how the spacing between the buncher and catcher cavities can be adjusted for maximum degree of bunching. Since the drift space is field free, we can write capital T is equal to T 2 minus T 1, where T 2 is the time when the electron entered the catcher cavity, and this can be written as L by V T 1. This is because the drift space is field free and the electron moves with the velocity V T 1. Now, we have already seen V T 1 is V naught into 1 plus beta I V 1 divided by 2 V naught sin omega t 1 minus theta g by 2, and therefore, we can write capital T is equal to L by V naught, we can write T naught, and 1 by this term can be written as 1 minus beta I V 1 by 2 V naught sin omega t 1 minus theta g by 2. Please note that this minus sign comes from the fact that beta I V 1 by 2 V naught, it is very less compared to 1, and therefore, 1 plus beta I V 1 by 2 V naught sin omega t 1 minus theta g by 2 raised to the power minus 1 can be approximated by this expression. And if you multiply both sides by omega, we get omega capital T is equal to theta naught. Theta naught is omega t naught. This is the DC transit angle, and then we have omega t naught beta I V 1 by 2 V naught, that means theta naught into beta I V 1 by 2 V naught, which we represent by x, and this x is the bunching parameter of the Klystron. Now, T2 is equal to T naught, the time of entry of the electrons in the buncher cavity, plus tau, the transit time of the electrons between the buncher grids, plus this term T naught 1 minus beta I V 1 by 2 V naught sin omega t naught plus theta g by 2. This is the transit time of the electrons in the drift space. So, sum of these 3 times give the time T2, the entry time of electron in the catcher cavity. Therefore, we can write d T2 is equal to, if we differentiate with respect to T naught, then we can write d T2 is equal to d T naught into 1 minus x cos omega t naught plus theta g by 2. This we obtain by differentiating this T2 expression with respect to T naught. Now, in the buncher cavity, a charge amounting to dq naught equal to I naught dt naught, this passes, and this amount of charge passes in the interval dt naught in the buncher cavity. The same amount of charge will appear at the catcher cavity at a later time interval dt2, and therefore, I2 into dt2 will give the same amount of charge that has passed through the catcher cavity, and we can write I2 as a function of T naught is equal to I naught divided by 1 minus x cos omega T naught plus theta g by 2. So, this expression we get by equating I 2 dt 2 is equal to I naught dt naught, and in terms of T 2 we can write I 2 T 2 is equal to I naught divided by 1 minus x cos omega T 2 minus theta naught minus theta g by 2. The beam current in the catcher cavity I 2, as we have seen, it is periodic. We have just seen that I 2 is periodic, and therefore, it can be expanded in a Fourier series. So, once we expand this in terms of Fourier series and find out the Fourier coefficients, I 2 can be written as I 2 equal to I naught plus summation of n equal to 1 to infinity 2 I naught j n nth order Bessel function j n n x cos n omega T 2 minus tau minus T naught. Now, this I 2 has several harmonic components. Because of the catcher cavity, because of the resonant behavior of the catcher cavity, this cavity will actually pick up the fundamental component, and the fundamental component of the current has a magnitude of 2 I naught j 1 x, and the maximum of this fundamental component occurs at x is equal to 1.841. So, j 1 x, the first order Bessel function, it attains its peak value for x equal to 1.841. Suppose the arrangement of the cavities are made in such a way that we are able to achieve the peak of this fundamental component, then from this relation x is equal to theta naught beta I v 1 by 2 v naught and theta naught is equal to omega L by v naught, and we also know that x is equal to 1.841. We get the optimum value of L. This L, what should be the spacing between the cavities so as to have peak of the fundamental current. This comes out to be 3.682 small v naught capital V naught divided by omega beta I v 1. So, at this spacing we get the maximum bunching to occur at the center of the catcher cavity.